Okay, so welcome back everyone to the online Graphs and Matroids seminar. Today we're happy to have Tom Zaslavsky from Binghamton University. So take it away, Tom, when you're ready.
Wait, if I take the computer away, then the talk's over. No, I'm sorry. So I promised to make the most beautiful unprepared talk of anyone except maybe Jack Edmonds. And this is because this is a very complicated subject. And I'm going to start at the beginning. So some of you will be completely bored for the beginning, and some of you may not know the background. And that's why I'm going to start by talking about a hyperplane arrangement. Okay, so first of all, the difference between these two orders of words is crucial to the whole subject, but I will explain later. Okay, what's an arrangement of hyperplanes? It's a finite set of hyperplanes. And I'm going to say affine hyperplanes because they don't have to be vector hyperplanes. Of affine hyperplanes, that's codimension 1 in R to the n. We could use a different field, but this one gives all the necessary information. I'm sorry? Okay, there was some funny beeping. Okay, now, what's a finite set of affine hyperplanes going to do in R to the n? Well, it does various structural things. It cuts the space up and it forms regions and faces and and so on. And what we want is a certain polynomial that I'm not going to explain, which we call the characteristic polynomial. Let's write script A for it because it's a nice letter. The characteristic polynomial. And this characteristic polynomial has a lot of information in it about the hyperplane. That's not the point of the talk. And the characteristic polynomial is P sub A of lambda. So some people use a different variable letter. Of course, you know that doesn't matter. And some people like to write chi, but I'm going to use chi for a chromatic polynomial, which is a different polynomial. It doesn't go with the hyperplane arrangement. So this is the characteristic polynomial. And the problem is to find the characteristic polynomial. So I'm going to show you a very simple example of how you can find the characteristic polynomial. Let's start with a hyperplane arrangement like this. Let's say in R cubed. Let's have two hyperplanes that look like this. Xi equals x1 equals x2, x2 equals x3. This is about as simple as you can get. Now, what do you this? I want to form the characteristic polynomial of this hyperplane arrangement. Of course, I'm using the equation to stand for the hyperplane. Everyone does that. So I can do this by graph theory. To find the characteristic polynomial, I will make a vertex set of 3 vertices. And I will treat this x1 equals x2 as meaning an edge between v1 and v2. And this hyperplane x2 equals x3 gives an edge between v2 and v3. And I calculate the chromatic, this is the graph gamma, and the chromatic polynomial of this graph is equal to lambda times lambda minus 1 squared. And that's easy to compute. It's easier than trying to compute the characteristic polynomial of the hyperplane arrangement directly, because it's so easy. So this is the philosophy behind the whole project. And that's true for any set of hyperplanes of the form xi equals xj. So I'm going to now draw a classification picture of different kinds of hyperplanes. So first of all, I seem to need to erase this example. But if you just remember the example, you'll see that it's a generalized in this diagram. Let's talk about two kinds of hyperplanes. So one kind of hyperplane is given by equations of the form xi minus xj equals 0. And the other kind of hyperplane is given by xi plus xj equals 0. But actually, I want to think of a larger class of hyperplanes. So you'll probably notice that there are a lot of hyperplanes that are not going to be in the classification. That's the third kind, and I ignore those. So there are only two kinds that I want to tell you about. So here is one kind of hyperplane. And if I took all of the hyperplanes of this type in n dimensions, let's say we're in R to the n. If I took all the hyperplanes of this type, I would have an arrangement corresponding to all the edges of the graph within vertices. And I can treat that hyperplane arrangement by looking at the graph. The graph is the complete graph. But what we get here is we get graphic arrangements. And the theorem is that the characteristic polynomial of the arrangement is equal to the chromatic polynomial of the graph. That is enough to say that you can compute everything you want in the polynomial by looking at the graph. And all the graph properties carry over to the arrangement. Okay, that's one type. And some people will know this is associated with the type A root system. Now, another type is if we want to go to the type B root system, for example, or C or D. Some of you know what that is. And what we need there is equations of a more general type. Now, in order to handle these equations with plus signs, we need to put signs on the edges. So let me show you here an example of a positive edge and a negative edge between v sub I and v sub j. And the positive edge corresponds to x sub I minus xj equals 0. And the negative edge corresponds to xi plus xj equals 0. Well, I'm not going to tell you why it goes this way. Some people think it's the other way around, but this is a perfectly correct thing. There's a good reason for it, but I'm skipping that. So what we are able to do is have graphs with signed edges. The positive edges are like ordinary edges, but the negative edges are different. And we can create an exact analog, a generalization, and we get arrangements that can be described by signed graphs. And we get the same theorem that the characteristic polynomial of the arrangement is equal to the chromatic polynomial of the signed graph, which can be defined and computed. Well, as you know, a chromatic polynomial of the graph can be computed in theory more than in practice, but if you pick the right graph, it's computable. So that's what happens for this generalization. Now, there's a matroid involved here, and the reason that the polynomials are the same is that the matroid of the arrangement is equal to the matroid of the graph. I should technically say isomorphic, but it's basically the same thing. And here, the matroid of the arrangement is equal to the matroid of the sign graph, which I'm not going to define. But we will get to talk about that. I'm showing you the general picture that led to the paper that I'm going to discuss. The general picture starts with this row. Let's say homogeneous. you notice that these are zeros. Oh, wait a minute. Let's move this line because now we want to generalize to arbitrary constants. So let's write xi minus xj equals a constant. This will be affine arrangements. And you'll notice that I'm only talking about two variables with a plus or a minus. And there's a reason for that. But let's stick with that. I'll tell you more about the background and you'll see why this is so important. The next thing is we can look at arrangements where we have xi minus xj equals a constant. And let's say mostly the people are interested in the constant being an integer. And we have a variety of constants to make an arrangement. We might have all the numbers from 0 to k, or from minus k to k, and other variations. So this type of arrangement is not described by a graph, but it's described by a gain graph. And I will have to explain what that is, but this is a generalization of a sign graph. And this gain graph, the gain graph is going to give us all the same information that we get from a graph in the case of this type A, or the sign graph in this other case. So this generalization exists. And let's see, what are some examples of the arrangements? I said type A, graphics, any graph. Well, some of these are, let me write additive because that's actually relevant. But some of these arrangements are the Cavallon arrangement, the Xi arrangement, and the lineal arrangement. And I mention these because some people know what they are, and other people will take my word for it, that they have been the subject of a great deal of interest over the past 20 years or so, or more, I forgot, 25 years. So they are interesting for reasons coming from algebraic geometry and who knows what. Combinatorics, they're related to combinatorics problems. So we want to know the characteristic polynomial of these arrangements. And in order to do that, it's nice to have a graph theory way of doing it. And the graph theory method is by an additive gain graph with a group, which I'm going to explain shortly. Actually, I'm going to write z super plus. That does not mean positive integers. It means the additive group of integers. And I'm emphasizing that because we are not interested in the multiplicative structure. The additive structure is very important. Well, okay, so these have been studied. And we might be interested in xi plus xj equals c. Or plus or minus to make it bigger. And this was not understood well enough. Now, let me give you a little more background. There's a crucial paper by Athanasiadis, who studied these examples. I forgot the year, but it doesn't matter because you can believe me that it was some time ago. And he studied these examples and calculated their characteristic polynomials. And he had some of this type also. He studied their characteristic polynomials, and he did it by what he called the finite field method. Part of my talk is that the finite field method is not actually a finite field method in this case. In fact, for these problems, he only used prime fields. And for these problems, he only used prime fields. So it's really the prime field method. And you'll discover that if you look at what people actually do. I'm not even aware that anybody has used non-prime finite fields. Now that actually is important because a prime is a number and a finite is not a number. Oh, oops. A finite field is not made up of integers modulo some number. A prime field is integers modulo the prime number. And in fact, the right generalization for the purpose of these types of arrangements is the integers modulo some positive number, not necessarily prime. Primality, it turns out, has nothing to do with it. I'm going to try to explain that, and that will give you some of the motivation for this generalization. But part of the motivation for the generalization is that I can explain why this finite field or prime field method works, and I can give more precise answers to Athanasis's computations. For this case, where we have xi minus xj, but I could not do it for xi plus xj. Here's where I explain the non-title of the paper. Non-title is signed gain graphs. Now, you might think that the solution to calculating these through graph theory, the xi plus or minus xj equals a constant through graph theory, is to combine signed graphs with gain graphs. And the obvious thing to do, I haven't told you what a gain graph is, so I'm going to do that shortly. It's a little more complicated than sign graphs, but the obvious combination is to take a gain graph and put signs on it. And people, including me, tried to do this for years and years and failed. We all failed. And then I got together with Laura and Ting, and Laura said, why don't we look at this? And it turned out to be that we were doing it backwards. You take a sign graph and you put gains on it. That's complicated. So now I'm going to tell you what a sign graph really is, what a gain graph really is. So you'll be able to see what the connection is. And this is part of the essence of this paper. Okay, so a sign graph each edge is either positive. We have a graph. Let's have a graph. Here's the sign graph. It's vertex set, edge set, and a sign function, which is a function from the edges to plus minus. Some people like plus one, minus one. The important thing is that we're multiplying them. So it's a multiplicative group. Some people like 0 and 1, but that's not actually good for the generalization, in my personal opinion, but it is just as good notation because we all know it's equivalent. If you take 0 and 1 modulo 2. But it's not the right way of looking at it for this general problem. It is the right way for some other purposes, by the way, so I'm certainly not putting it down. But what we have here is a sign function. Now let's talk about a gain graph. A gain graph, let's call it phi or phi. And we have a group. I didn't write the group in the definition because I didn't feel like it, but it's there. And we have a group G, and we have for each edge, here's an edge, and let's call it VI, VJ, and we'll call this edge E. And I'm now going to tell you what the group element is assigned to this edge. In this direction, the group element is C. And in this direction, let's make it an abelian group because that's all we're going to be able to talk about really. An abelian group, and in this direction, it's minus C. So the value of the gain depends on which way you go along the edge. That's what makes it a gain as opposed to a weight. That's my personal way of classifying things. So when you have a gain graph and the group, for example, could be the additive group of integers, which is what gives rise to these arrangements that people are interested in. Now, let's see what's going on here. We've got an orientation of the edge. So if we travel along the edge, we know which way we're going. And we might even have a whole path like this, and we might have some other edges. Oops, I'm sorry. We have an orientation of the edge for the sole purpose of reading the value of the gain. That's the only thing that's significant. We are not fixing a direction of the edge. So this is not directed graphs. Directed graphs are actually quite a different topic. So let's say we have here A, and here B, and here we have D, And of course, that would mean in the opposite direction, we have minus a, and I won't continue because you can see the pattern. Now, this is a circle. Some people say cycle, but cycle means 5 different things in game theory, so I'm calling them circles. We're going to call them circles, by the way. So here's a circle. And we would like to calculate the gain of the circle the way we calculate the sine. Well, I didn't mention the sine. For a sine graph, if we had a circle, I should show you this because it's so much simpler. Suppose that plus, minus, minus, plus, plus. And this is the circle. The sine of this circle, the sine of the circle is equal to the product. So I'm here, the group is additive. So the gain of this circle is the sum of the gains. Okay, I have to be careful because they're not in alphabetical order. C plus A plus B plus D. Oh, actually, it's abelian, so it doesn't matter. But still, it's more elegant this way. And the group doesn't have to be abelian, but we're going to get to where it does have to be abelian later. So we multiply or add, in this case, the gains around the circle. Now, what's significant about the gain of a circle? Well, the number would depend on the direction. If you reverse the direction, you're going to invert the value of the gain, in this case, negate. In this case, it won't make a difference with sine graphs. But in general, for gain graphs with arbitrary groups, it makes a big difference. But I don't care, because all I want to know is that I'm looking for a good color for this. Here. C is balanced. This is for sine graphs if the sine is positive. And in the gain graph case, C is balanced if the sum, the gain, is equal to 0. This is the neutral element, or we could call this neutral because some people like to call it neutral. I'm on both sides. So let's call it neutral because we get the neutral element. Now that doesn't depend on how you compute the gain. Every change you make, like going in the opposite direction, doesn't change whether it's 0 or not. This is where you get the connection with the arrangements of hyperplanes, because it turns out that there's a matroid for a sine graph, and more generally for a gain graph, where I will now have to make a little more space. Let's make a little space here. The matroid has so we have let me start with the point set. The matroid m of this phi has actually I call it f because it's a certain, but this is not important. I'm going to explain why we're not quite using the whole matroid. The matroid has point set. Let me say is on the edge set. The elements of the matroid are the edges of the graph, and the rank function of a subset of the edge set is equal to the graphic rank function, which is the graphic matroid, the ordinary matroid, cycle matroid. If S is balanced, I will define that in a moment, and it's, let me put that equal sign here, it's greater if S is not balanced. Okay, I defined balance for a circle, but in general, we say S is balanced. That's any edge set if every circle in it Now, balance means that it behaves like the ordinary graph in terms of matroids and other properties, including coloring. The unbalanced sets are the ones that behave differently. And I'm not going to give you any formulas because I really don't want to get into that. But the idea is that we're getting non-graphic, we're getting gain graphic, or sign graphic in this special case, if S is unbalanced. And the behavior is different. The matroid is bigger in a sense. It has a bigger rank function. Now we can use this matroid to generate a characteristic polynomial by taking the chromatic polynomial of the graph, and the characteristic polynomial of the matroid will be equal, well, but now I'm sort of lying. Yes, let me write down a couple of things that we have to be careful about. If I turn this way, this will work well. Okay. Let's look a little more closely at what happens. First of all, when you have affine hyperplanes, here's some hyperplanes. They do not intersect. Well, let's have another hyperplane just for fun. So here we have not a whole matroid, because a whole matroid would have to have an intersection out at infinity. The matroid here of this arrangement is, well, now I'm being a little sneaky. The matroid of the arrangement has point set A, the set of hyperplanes, and the rank function of a subset is equal to the codimension of the intersection of that subset. That's the standard rank function for hyperplane arrangements, except that if we have no intersection, we get more complicated, and it's undefined if the intersection is equal to the empty set. This is for affine hyperplane arrangements. You won't run into empty intersections if all your hyperplanes go through the origin, and then you'll just have a nice matroid. But what we really want is, we call this a semi-matroid. Our DLab worked out some axioms for this based on geometric semi-lattices by Wachs and Walker, and I'm just mentioning these because they are important in the theoretical background. So we call this a semi-matroid because we don't actually talk about a set of hyperplanes whose intersection is the empty set. So we only talk about the ones whose intersection is not the empty set. Now, when I'm doing arrangements that come from a gain graph, like what I was showing you over here, when I look at the graph, if I get an unbalanced circle, that set of edges is going to have empty hyperplane intersections. So every hyperplane in my type of arrangement, this type here in this lower left corner, every such arrangement is going to have hyperplanes that might not intersect, or subsets that might not intersect. And the edges that correspond to this will be precisely the unbalanced edge sets. Well, it turns out there's a special kind of chromatic polynomial which goes with this. And I'm going to say we have a chromatic polynomial phi sub phi of lambda. That's the chromatic polynomial. And we have something called the balanced chromatic polynomial pi star of lambda, which counts only certain kinds of colorings. And you can do this. You can actually compute these things in nice graphs. So this is the polynomial that goes with an affine hyperplane arrangement of this type. So for xi minus xj equals c, let's say arrangements of this type, by which I mean that every hyperplane has an equation of this type. For arrangements of this type, we want to have the, let me start the other way. The characteristic polynomial of the arrangement is equal to the, not the chromatic polynomial, but the balanced chromatic polynomial of the gain graph. And this enables you to compute things more easily. And I think the basic way of thinking about it is that you can draw a picture of a 10-dimensional hyperplane arrangement if you only need to draw a graph, because you can draw a graph with 10 vertices. Okay, so using gain graph coloring, we can compute the characteristic polynomial of this affine hyperplane arrangement. This is the type known as affinographic or deformations of type A. I'm not going to write that down because I don't have room. But how are we going to deal with the plus sign? The plus sign looks like we should have signs like xi. Let me write this down because I think I forgot to actually write it. Minus edge. Oh, I did write it down. Okay, so that's the type of equation for a plus edge, but for a minus edge, this is the type of equation. And it looks like we ought to be saying here that we allow negative edges with gain C. And yes, that's true. But you can't just put the sign on the gain. You have to do something more subtle. So here is where we start getting complicated. That was the simple part. The complicated part is that we have to orient the sign graph. Now let's go back to the definition of a gain graph. When you look at a gain graph, you will see that the gain of the edge in this orientation is C, and in this other orientation, the opposite one, it's minus C. Well, that's how a positive edge behaves. A negative edge has to be oriented in order to put a gain on it, which is what we really want to do. I erased that part, but that's why we put a gain on a sign graph. And in order to do that, we have to know how to orient a negative edge, because the orientation of the edge as we strike the edge and go across it, if you think of traveling around a circle, the orientation tells you whether you take the gain or the negative of the gain. So we are actually putting, this is the secret, putting gains on oriented sign graphs. The same way you put gains on, now by oriented, I mean there's no fixed direction for an edge. The orientation tells you which way to read the gain. So let's erase all this, and then we're going to solve this problem by showing how to put gains on an orientation, on an orientable sign graph. All sign graphs are orientable, so it will be every sign graph. Let's see, I think I will just erase all this, and now we're going to start from scratch more or less, because we're going to have to rebuild the whole theory with the generalization that instead of working with graphs, orientable graphs, we're working with orientable sign graphs, and you will soon see, if you don't already know, that that's kind of complicated. So now I'm going to start back in this corner, and I'm going to show you, and I'm going to have a little sip of coffee so I don't stop in the middle. I'm going to show you an orientation of a graph edge. Well, you know this point. Okay, that's a plus edge. A minus edge, so it's like an ordinary, a plus edge is an ordinary edge for most purposes. Okay, a minus edge orients as there are two orientations. I'm still holding this as a secret. Two orientations, either this version or this version. Look at that, an arrow at each end. I call this extroverted because it looks like it. And of course, this would have to be introverted. But if I spell it right, it'll be better. Okay. Oh, wait a minute. Two arrows, independent arrows at each end. Oh, but they're not really independent because it's a negative edge. They're oppositely directed. So let's have two arrows for the positive edges. That's what the two arrows. So there's an arrow at each endpoint of an edge. When you have a sine graph with positive and negative edges, every edge gets two arrows, one at each end. And if they agree, that depends on what you mean by agree. Okay, if they point the same way, then it's positive, and if they point opposite ways, it's negative. And this is actually what Edmonds introduced as called a bidirected graph. So it turns out, and people say that Hefter had something like this many years before, but it really took off, as far as I know. My knowledge is not great. When Edmonds introduced this in connection with matching theory. So this is a bidirected graph. It turns out that precisely a bidirected graph is identical to an oriented sine graph. In fact, the bidirected graph, where you fix all the bidirections, is the generalization of a directed graph, where you fix all the directions. But we're not fixing them, we're only using them for the purpose of reading the value of a gain. Now, suppose I want to put a gain function on the edges of a sine graph. Let's have a sine graph. Sigma is, okay, let's see, V, I gotta know this. I've been doing this for longer than I've been alive. VE sigma, okay. So let's have a sine graph, and I will orient this sine graph before your eyes. Look. Oh, I'm not orienting everything in line. Okay, so here's another edge, and I think we could even have a loop. Let's have a loop. And let's have a negative loop. By the way, for the Matroid people, a positive loop, just as an ordinary graph, is just a graph loop. A negative loop is much more significant. So now I'm going to orient this for the purpose of assigning a gain. So I'm not actually going to fix the orientation. I can travel in either direction. So let's just orient that way, and it'll have gain A. Let's say the gain group is the additive group of integers. And the reason is because that's the one that I'm most interested in. But it could be the real additive numbers. It could be anything. Actually, we probably don't want to use a field of characteristic 2 because then plus and minus are the same. But otherwise, anything. So here's another example. Let's say that has gain B. Oh, this is not going to be trivial anymore because we're not just treating it as a loop, but as a loop with a gain value, and that makes a difference. And here we have, let's do it this way, this extroverted loop. And let's call that gain C. And let's make this one an introverted edge with gain D. And here we have another edge with gain E. Now, this means if I flip the orientation, the gain is minus C. I'm going to show you how that matters. And here we have, let's say, another one, and here's another one. So where am I? E, F, and G. Okay, so now let's try traveling around a a circle. Let's pick a sample circle and travel around it. The gain of this circle is equal to B, or possibly minus B. Now, remember, what I care about is whether the gain is 0 or not. So it doesn't matter whether it's plus or minus B. Now, let's look at this circle. Here's a nice little triangular circle. Maybe I'll start at G. Oh, wait a minute. If I'm going that way, I'll get minus G. Oh, what do I do here? Which way do I treat E? It turns out that whether these two arrows agree with each other at the common vertex tells me what to do with E. Since I'm going this way, and then I'm going against this, I'm going to have minus E. And I come out here, and then I'm coming out this way, plus F. And I hope that I'm right, but I have to admit that I forgot to check the exact rule. You have to be very careful because you get huge complications with this. Anyway, I now have a circle where I have computed the gain. And the gain is minus G minus E plus F, unless I made a mistake and it's minus G plus E plus F. But I think this is correct because you notice here I have 1 point. This is a negative circle. And when I bidirect it, if my arrows agree at the other vertices, if they agree here and they agree here, they have to disagree here because it's a negative circle. So we will have an odd number of disagreeable vertices. Well, okay. If this sum equals 0, then that is called a neutral circle. So let me write this down. Neutral if the gain equals 0. So I'm going to say balanced for well, there'll be positive circles and negative circles in the sign graph, neutral and non-neutral circles in the gain part. But there's more to it than that. I'm going to have to tell you about the matroid of the sign graph and the matroid of the gain sign graph. And then we'll show those pictures that Zach has and we'll be done because it's complicated enough and time is running out. Okay, so let's take a walk. Instead of a circle, we could take any kind of walk, like start here, walk down here, and then around here, and then up here, and then down here. And we would compute the gain of this walk according to the same rule I was using before. If I come down here, I'm taking minus A because I'm going against the direction of that positive edge. And then I come to a disagreement of the directions. So I will reverse the sign. Let's see, what did I do here? I think okay, I had minus G here and I kept the minus sign because the arrows agreed. Here the arrows disagree, so my minus sign should become a plus sign. So I will get plus D. And then I go down here and I hit the arrows agree. So I'm going to do plus C. And if this is not exactly true, then somebody should fire me. But after C, we do F, and if the arrows agree, we go out of C and into F. So I will still keep the plus sign. And I think the actual rule might be more complicated, but there's no point in making it even more complicated. So here we hit a disagreement. So I will subtract G, and then I subtract E because it agrees. And then, oh, I stop. Okay, so this is a walk. The gain of the walk. By the way, why gain? Some people call these voltage graphs. They're back to the gain graphs originally. They don't satisfy voltage laws. And some people were confused. So I thought we need something that has no laws. Gains have no laws, electrically speaking. Anyway, so we can look at the gains of closed walks, and we're going to be wanting the gains of open walks. We don't care that much, but closed walks we do care. Now, I'm going to show you the matroid of the sign graph, and then I'm going to show you how we use the circuits of the sign graphic matroid as the basis for describing the circuits of something is, oh, I know, I've got it backwards. As a basis for describing the circuits of the gain sign graphic matrix. Okay, here's a nice open board. This left-right business is, what is going on? It's supposed to work better. Oh, like that. Okay. No, bad. Pardon me while I adjust my scanner here. Okay. Matroid. Actually, this is the frame matroid. Of the sine graph. I mentioned the rank function, but now I'm going to be specific. I'll give you the circuits because that's what turned out to be the hardest part. And I have to give credit to Ting because she worked this out. I don't know how she did it, but she worked out this list, and then I sort of wrote it up nicely. And here are the circuits. Okay, so any circle, positive circle. Excuse me, positive circle. So this is another instance where a positive edge is just like an ordinary graph edge, because if it's all positive, all circles are positive. But if it's not all positive, still a circle whose sine product is plus is just a circle. But here is the other kind. A negative circle and another negative circle and a connecting path. Oh, the connecting path could have length 0. So just to show you. And this type is also a sine. In fact, that's the complete list of sine graph circuits. Now, let's put gains on these. So we're going to have some gains. And I like a bright yellow color. So let's have gain G1, G2. Well, which way? Which way? Uh-oh. So let's assume these are all positive edges just to make it simple. And G3 and so on. And finally, G sub L. L is the length of that circle. It's supposed to be a sort of general circle. And so the gain is in this picture G1 plus G2 up to G sub L. And it's equal to 0. That's a neutral sine circuit. Suppose it's not equal to 0. Then it's not neutral. Actually, we call it frustrated. That's a term that comes from physics. But it was so good that I had to adopt it. And so we have here two kinds of positive circles, neutral and non-neutral. If it's neutral, it's going to be a gain circuit. If it's not neutral, it's not going to be a gain circuit or a gain sine circuit. It's going to be something that's part of a circuit possibly, but that's where I'm not even going to try to draw them. Let's talk about these handcuff types or barbell, if you prefer. We are going to take a trip around this. Let's start here just to make it a little simpler. We're going to take a trip around this and we're going to calculate the gain of this walk. So this walk, that's what we did here. We took a walk around the circle and we calculated the gain. It was 0 or not 0. 0 is neutral and non-zero is non-neutral. Okay, and then we finish here. Notice we've gone twice, once in each direction on this part. And on the circles, we've gone around once. And you might go the other way, but it turns out that if you're very careful, now all these gains, there are going to be negative edges here. All these gains have to be calculated carefully according to what I was showing you back here, where I actually looked at the individual edges and how they were oriented and what their signs were, showed you how to orient them. But now I'm ignoring that part, just to say we can compute by that method the gain of this circuit walk. So we have a circuit walk here. I should really, just for consistency, I should show the circuit walk. So that's the circuit walk for a circle, and here's the circuit walk for the handcuff, or the same thing here, basically. And we want to know if the gain is 0, that's a neutral sine circuit. And if it's not 0, it's a non-neutral or frustrated sine circuit. The neutral sine circuits will be circuits of the gain sine graphs. The non-neutral sine circuits will not be circuits, they will be independent. And we need to look at even bigger sets. And now I think it would be a perfect time for Zach to show the first page of the circuit pictures, and you can look at the circuit pictures. The problem with you guys is you should get out the people sitting here in front of me. Thank you. Raise that up so you can see the figures. And okay, no, both figures. Right. These are the sine circuits that become circuits. Now, you should pull out some kind of viewing machine and sign into the link is on the seminar website. And that doesn't work. I'm willing to show this to you, but it may be hard to see. Okay. You have it. Yes, it's an email. Right. Okay, so that's the simplest set of gain sine circuits. Okay, Zach, can you go to the next page? Okay, now we're getting to more, look at the theta graph. That's a theta graph for all, if two of these, so let me think. In a signed theta graph, that's the one we have on the left top here. In a signed theta graph, you can only have an even number of negative circles. Now, the example, if you have 2 negative circles, then you're going to have a positive circle, and so it won't be a sine circuit. This is a special case where we have all positive circles because the third circle has to have the product of the other 2 signs, and that's in A in figure 8.3. And we calculate some sort of gain function on this, and if it's 0, well, then if it's 0 on any one of the circles, then we actually have a gain sine circuit properly contained in this theta graph, one of the circles. But if it's not 0 on any of the circles, then the whole thing will become a gain sine circuit. And similar rules apply to part B in 8.3. And then you can look at 8.4. Well, it's, oh my, it gets complicated. You see, these are a few of the examples of circuits. Let's go down a little bit and see if there's another one. Yep, there's some more. Yep, there's some more, right? And these are, if none of the positive circles has gain 0, is neutral, and none of the handcuffs with negative circles has gain 0, then the whole thing is a sine circuit. Sorry, a gain sine circuit. And let's see, is there another figure? I think there might be another one, but I'm not sure. It looks like yes, there's another one. Okay, there are 2 more. And you notice a K4 finally got in there. K4 had to show up. And I think that's the complete list. So we call those hypercircuits so as to distinguish sine circuits from hypercircuits. Anyway, I think if you go to the next page, you won't find any more. And I was right. Okay, thank you. Now, I think I've shown you enough to see that the Matroid is fairly complicated. But being able to work out this list was quite a feat. Well, thank you. That's everything I wanted to say. I'm ready for any questions, if anyone has a question. And I will be happy to not answer any ones that I can't.
Okay, so on the count of 3, let's unmute and give Tom a round of applause. 1, 2, 3. Okay, are there any questions?
Yeah, I
Right.
was just wondering if,
The whole purpose
Oh.
was to answer that question mark there. That's gone there. Okay, sorry.
I was wondering if, so are there representable matroids, and what's the representation look like? So if I choose appropriate groups and such, then are there natural representable matroids sitting here associated with these objects, and what's the representation?
Well, you can use any field that distinguishes plus from minus. If you are representing over a field that doesn't distinguish plus from minus, then you're just doing gain graphs because the sign part disappears.
Right, so that would be the frame matroid of the game.
So what we're doing is we're constructing a matroid, the gain sign graph matroid upon the frame matroid of the sign graph. So if the sign graph is just balanced, then it's just based on the graph. And that was not hard to do. By the way, I didn't explain why I disagree with the finite field name, because maybe I should explain that, but if anyone wants me to, I will in a question.
But
Did I ask a question, Jim?
not really yet. Okay, so let's take GF5.
Yes.
So what am I doing? So I take that. So I've got this underlying frame thing, and then is it a lift of a frame matroid, or is it?
Yes, it is. It's a single element. It's actually a single element extension. If you do the full Monty, there's an kind of ideal element which I haven't mentioned, which you should have in every lift matroid of a graph. Every graphic lift matroid also has an implicit ideal element, and it's the same here. It's a generalization of graphic lifts. It's framed lifts, if you like.
Okay, so we're dealing with lifts of frame matroids.
That is correct.
Okay, thank you. That's exactly what I wanted to know.
Okay, good.
Any other questions?
Yeah, I mean, you were motivated by calculating these characteristic polynomials, but you only do it for very special hyperplane arrangements.
Of course, right. Essentially graphic ones.
Yeah. So there's nothing you can do unless you're essentially getting some underlying graph from the hyperplane arrangement.
Yes.
Yeah. And do the people who do hyperplane arrangements really care about these specific hyperplane arrangements?
There are dozens and dozens of papers about them. I mentioned the names Catalan, Shi, and Lineal, and there are others. There are big papers by Postnikov and Stanley. Athanasiadis' original paper did these kinds of arrangements. That's what motivated me to try to find a combination of signs and gains, which I failed to do for a long time. But anyway, yes, Athanasiadis' paper has been very influential. He calculates quite a number of these examples, and they are all of the gain signed type. Yes, so there's a huge literature on this.
Okay, and can you explain?
Huge is dozens.
Okay, in matroid theory, that's huge.
Yes. In hyperplane theory, it's actually pretty substantial too.
Yeah, okay, so explain to me why it should be prime field and not finite field.
Okay, I would like to explain that because it's my propaganda point. First of all, if you look at the papers, I don't remember a single instance where a non-prime field was used or needed to be used. Athanasiadis started this. He only used prime fields. Okay, so that's the first element. But now I'm going to explain why it's not really fields at all. It's groups, it's additive groups, finite additive groups. Let's take a look at, by the way, I'm going to cite a paper for this, of which I am the fifth author. So I think that's amusing. What did I do on my chart? Okay, this will be good enough. The paper's title is long, and I will give you the first part. This paper discusses how to do this in detail. And it treats the Xi lineal and Catalan arrangements, I believe, if I remember correctly, showing you how to do this. Okay, let's take a look at this. We want, so the fundamental thing is we want to calculate the balanced chromatic polynomial of a gain graph. Now we have here we have an integral gain graph. In other words, it has gains in the integers. This is what all these papers are about. They're all about different kinds of integral affinographic. They call them deformations of type A and type B, but I call them affinographic because they're affine translates of graphic hyperplanes. So we are looking at a Z plus gain graph, which means we have hyperplanes of the form xi minus xj equals c. So they're all of this form. The c can be a variable. I mean, it could take many values, but they're all finite sets of hyperplanes. Okay, now so this corresponds to an edge, which I would say, no, we're not doing signs. So this will have gain C in that direction from V sub J to V sub I, or minus C in the other direction. And that's the graph counterpart to the hyperplane. Now they're looking at hyperplanes that correspond to gain graphs with the additive integer as the gain group. Now, what Athanasius is essentially doing is he's saying, let's calculate this same gain graph. He takes his hyperplanes modulo P, the prime. He never uses prime power. He takes the whole thing modulo P. So this C is taken modulo P, and he does some computations which are actually essentially computing the balanced chromatic polynomial of this gain graph at P. So he's not even computing the whole polynomial. And he shows that these are equal at lambda equals P if P is large enough. Well, by looking at it graphically, I can tell you that this is independent of having a prime. It could be any integer, positive integer, any sufficiently large positive integer, and I can tell you in terms of the graph exactly how large and expect exactly which values of m this equality holds for. It doesn't hold for all values of m or for all primes necessarily, but it holds for all sufficiently large ones. It holds for all m greater than the largest gain of a circle. I can't spell, okay. Largest gain of a circle. In fact, even more than that, this equality, so you see, you can calculate for infinitely many values of m. This is a single polynomial. This might not be a single polynomial, but it turns out that when you substitute m, it's going to agree if m is large enough. In fact, it is the same polynomial, but I would have to do much more work to show that. So I'm not going to explain that. But in fact, for all m greater than the largest gain. In fact, for all m such that m does not divide any circle gain. That's all you need. So if all the circle gains are even, then any odd value of m will give you equality here, including 1, 3, 5, not even necessarily large. If all the gains are in the set, circle gains are in the set 1, 2, 5, 6, 7, then 3 and 4 will give you agreement, 5 and 6 will not, and 8, 9, 10 up to infinity will give you agreement. So his method works. It's a good method, but it doesn't depend on prime numbers for the arrangements of this type. And that's the only ones he did. And many other people have used the same method, and in almost all cases, not all cases, but they're doing the same type of arrangement of hyperplanes, and the same rule applies that it's not really primes, it's really sufficiently large moduli taking Z mod n. That's my argument.
Okay, thanks.
You're welcome. And you'll find it explained more carefully in here.
Thanks, Tom.
Oh, yeah, thank you for asking. That's one of my favorite tricks. It's an interesting thing. You really get more in some sense by using the graphic approach.
Okay, so I think I'll stop the recording and we can continue with some more informal discussion.
Okay.